A number of experiments were performed and it was shown that the mass of one proton is 1.67 into 10 to the power minus 27 kg. Hydrogen atom, it has only one proton, it has no neutrons, and it has one electron. But the mass of a hydrogen atom is 1.67 into 10 to the power minus 27 kg, which is the mass of a proton. We know that the mass of electron is quite negligible as compared to the mass of proton. That is why we do not consider the mass of electrons. And this is the reason why the mass of a hydrogen atom is equal to the mass of proton, which is 1.67 into 10 to the power minus 27 kg. Now this is a very complicated number. So to avoid using these numbers, scientists prefer to use simpler numbers. So in chemistry, we use atomic mass unit to measure the weights or the masses of these light particles. This atomic mass unit is abbreviated as AMU. So the mass of one proton is taken to be 1 AMU. That is why the mass of hydrogen atom, which contains one proton, is 1 AMU. We neglect the mass of electrons because it is quite negligible as compared to the protons. So this is the lightest element. It contains only one proton and its mass is 1 atomic mass unit. Now, how do we calculate the mass of other elements? Other elements have different numbers of protons and neutrons. It's not very easy to calculate the masses of all the elements, but it is easy to compare the masses of the different elements with one particular element. That is why whenever we have to calculate the mass, the relative atomic mass is calculated. Relative means it is in reference to the mass of some other element. This relative atomic mass is also known as atomic weight. John Dalton was the first scientist to propose that the masses of the other elements can be compared to the lightest element, which is hydrogen. Its mass is taken to be 1 atomic mass unit. So the masses of all the other elements can be found out by comparing it to the mass of the lightest element, which is hydrogen. So when hydrogen combines with oxygen, it forms water. The mass of water or one molecule of water is 18 atomic mass unit. We know that the mass of hydrogen is 1 atomic mass unit. There are 2 hydrogens, so we get 2 into 1 atomic mass unit. Now this 2 into 1, we do not know the atomic mass of oxygen. Let's take it to be X. And we know the atomic mass of the water, or one molecule of water, which is 18. So we get the atomic mass of oxygen is 18 minus 2 or 16 atomic mass unit. So the atomic masses or relative atomic masses. Now this is the relative atomic mass. The relative atomic mass is also abbreviated as RAM. The relative atomic mass of oxygen is 16 atomic mass unit. So the masses, the relative atomic masses of the other elements are found out by comparing it with the lightest element, in this case hydrogen. So how do we do that? When hydrogen combines with different elements, we get the atomic masses of that species. So that is how we get the relative atomic mass of the particular species. But it was found out that hydrogen does not react with most of the elements. That is why we shifted to another element. Let's see what is the atomic mass of carbon. We have one hydrogen atom. Let's add a carbon atom. So a carbon atom is heavier as compared to hydrogen. Let's add more hydrogen atoms. We have now 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So the mass of 12 hydrogen atoms is equal to mass of 1 carbon atom. This is why the mass of one atom of carbon 12 is 12 atomic mass unit. It is 12 times heavier than one hydrogen atom, and this carbon 12 is taken as the reference to calculate the relative atomic mass of the other elements. This is because carbon easily reacts with most of the elements, and to find the atomic masses of all the other elements becomes easier when we take carbon 12 as the reference. And the mass of one carbon 12 atom is 12 atomic mass unit. So based on this, that is taking carbon 12 as the reference, we get the relative atomic mass of all the elements, that is calculated by taking the mass of one atom of the element and dividing it by mass of one carbon 12 atom. So the relative atomic masses of all the elements can be calculated by taking carbon 12 as the reference, and that is calculated by taking the mass of one atom of a particular element and dividing it by the mass of one atom of carbon 12. So based on this, the relative atomic masses of different elements were calculated. So for hydrogen, the relative atomic mass comes out to be 1 by 12. For carbon, it becomes 1, since we are comparing it with carbon itself. For nitrogen, it becomes 14 by 12, and so on. So we observe that these numbers, that is these denominators, make the relative atomic masses a little complicated. So what do? We take 1/12 the mass of one carbon 12 atom. The mass of one carbon 12 atom is 12 atomic mass unit. If we take 1/12 of the mass of one carbon 12 atom, we get 1 atomic mass unit. So this makes it easier to calculate the relative atomic masses of the different elements, and we do that now by taking the mass of one atom of the element, dividing it by 1/12 the mass of one carbon 12 atom. So when we use this formula and we calculate the relative atomic masses, we see that all the denominators, that is all the denominators which were 12 are now removed, since we removed the number by using 1/12 the mass of one carbon 12 atom. So we get the mass of sodium equal to 23, the relative atomic mass of aluminium coming out to be 27, and so on. So these are the relative atomic masses of the different elements. So we have seen that the relative atomic masses, which can be abbreviated as RAM, and which are also known as the atomic weights, this is the number of times one atom of the element is heavier than 1/12 the mass of one carbon 12 atom. So if we have the relative atomic mass of sodium, which is equal to 23, this means that one atom of sodium is 23 times heavier as compared to 1/12 the mass of one carbon 12 atom. Let's look at the chlorine isotopes in nature. There are two chlorine isotopes in nature, 35Cl17. So we know how do we read this. The superscript is the mass number. So we have the mass number of this isotope as 35. The other isotope of chlorine is 37Cl17. So the superscript gives us the mass number. So the mass number of this chlorine isotope is 37. So now, what should be the relative atomic mass of chlorine? Should it be 35 or 37? We know that one element cannot have two relative atomic masses, right? So it should have only one relative atomic mass. Now, to calculate that, we need the relative abundance of the two isotopes. The relative abundances of the two isotopes are in this ratio. This means the first isotope is 3 times as abundant as the second isotope, which is 37Cl17. Now to calculate the relative atomic mass of chlorine, we take the mass number of the first isotope, multiply it by its relative abundance, We add it to the mass number of the second isotope, multiply it by its abundance, and we divide the whole by the total abundance. So when we do this, we get the relative atomic mass of chlorine. So the relative atomic mass of chlorine is not 35 or 37, but taking into account all the isotopes, we get the relative atomic mass of chlorine to be 35.5 atomic mass unit. We know that the mass number of any atom is the total number of protons and neutrons which are present in an atom. So now what's the difference between the mass number of an element and its relative atomic mass? Let's see. The mass number is simply the number of protons and neutrons in a particular atom. But when we talk of the relative atomic mass, we take into account all the isotopes which are present in nature. So the mass number gives us the number of protons and neutrons for a particular atom or for a particular element. But whenever we are talking of the relative atomic mass, we always take into account all the isotopes of that element which are present in nature. So when we talk of chlorine, we see that the mass number of the first isotope is 35. The mass number of the second isotope is 37. But this is not the relative atomic mass of chlorine, and this is not the relative atomic mass of chlorine. The relative atomic mass of chlorine is calculated by taking into account the relative abundances, and this is how we get the relative atomic mass of chlorine to be equal to 35.5 atomic mass unit. So whenever we are calculating the relative atomic mass of a particular element, we take into account all the isotopes of the element which are present in nature. Like the relative atomic mass for a particular element, we have the relative molecular mass for a compound or for a molecule. So the relative molecular mass can be abbreviated as RMM, and this is also known as the molecular weight. This shows the number of times one molecule of a substance is heavier than 1/12 the mass of one carbon-12 atom. So like the relative atomic mass shows the number of times one atom of an element is heavier than 1/12 the mass of carbon-12 atom, the relative molecular mass shows the number of times one molecule of the substance is heavier than 1/12 the mass of one carbon-12 atom. Let's look at water. We know that the relative atomic mass of hydrogen atom is 1 atomic mass unit, and the relative atomic mass of oxygen is 16 atomic mass unit. Now, if we have to calculate the relative molecular mass of water, which contains both hydrogen and oxygen, how do we calculate that? We see there are 2 atoms of hydrogen. And we know that the relative atomic mass of each hydrogen atom is 1. And we have 1 atom of oxygen, and the relative atomic mass of each oxygen atom is 16. So when we calculate this, we get 2 plus 16, which is 18 atomic mass unit. So the relative molecular mass of water, which contains both hydrogen and oxygen, is 18 atomic mass unit. And this shows that one molecule of water is 18 times as heavy as 1/12 the mass of one atom of carbon-12. Now, what should be the relative molecular mass of ammonia? We are given the relative atomic mass of nitrogen and hydrogen. So if we have to calculate the relative molecular mass of ammonia, we add the relative atomic masses of each of the elements. So we have 1 atom of nitrogen, and the relative atomic mass of nitrogen is 14. We have 3 atoms of hydrogen, and the relative atomic mass of each hydrogen atom is 1. So when we calculate, we get 14 plus 3, which is 17 atomic mass unit. So the relative molecular mass of one molecule of ammonia is 17 atomic mass unit. Similarly, if we have one other molecule, which is NH42SO4, and we have to calculate the relative molecular mass of this molecule, we simply add the relative atomic masses of each of the species. Now, in this case, we have 2 atoms of nitrogen, each having the relative atomic mass 14. We have 8 atoms of hydrogen, each having the relative atomic mass 1. 1 atom of sulfur, each having relative atomic mass 32, and 4 atoms of oxygen, each having the relative atomic mass 16. So to calculate the relative molecular mass of one molecule of NH42SO4, we now add each of these. So let's calculate. When we calculate and add this, we get 6 plus 4, 10 and 12. And we get 6 plus 3, 9, 10 and 13 atomic mass unit. So the relative molecular mass of one molecule of NH42SO4 is 132 atomic mass unit. This shows that one molecule of NH42SO4 is 132 times as heavy as compared to 1/12 the mass of one carbon 12 atom.